Munmi.
Yes, sir.
It's the time. You check our officials are already joined or not.
Yes, sir. Yes, sir. Sir, Dean sir has joined.
Okay. And HOD sir.
Sir, let me check, sir. Just wait.
HOD sir joined.
Okay.
Sir, Dean sir is there or what? I can find where.
Uh,
So we'll start once the Dean sir has joined.
okay.
Yes, sir.
So you take the permission of Honorable Dean sir and our HOD sir.
Yes, sir.
And Rakesh Punendu, you people are also
Yeah, I'm there. I am
Okay.
there in the meeting.
We are sir, we are here.
Okay. Okay.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good
Good
morning,
morning,
sir.
sir. Good morning.
Yeah,
Sir,
very good morning to all of you and
good
all
morning.
the speakers.
Good morning, sir. Proceed to sir. Shall I start, sir?
Uh, our Dean sir, shall we start, sir? Pankaj sir.
Yes, good morning. Yeah, Pule.
Good morning, sir.
Good morning,
Yes.
sir.
Shall we start, sir?
Yes, sir is there. So, yes, we should. I think we should.
Okay.
Yeah.
Okay, Munmi, please start the session.
Yes, sir. Yes. Good morning, Excellencies, distinguished delegates, ladies and gentlemen. Thank you very much for joining our webinar on recent developments in big data, cloud computing, quantum computing, and hardware technologies. I am Munmi Gogoi, and it gives me great pleasure to extend to you a very warm welcome on behalf of Department of Computer Science to this 2 days webinar on recent development in big data, cloud computing, quantum computing, and hardware technologies. And so just a quick note, let me tell you that this session will be recorded and will be streamed in YouTube. So please be aware of it. If you have your camera on, make sure it is turned off. If you do not want to share your video in social media. Well, Dean William R. once said, the aim of education is the knowledge, not of facts, but of values. In the occasion like this, we get the opportunity to test our knowledge and understanding. This webinar aims to shed some light on the growth of new computing and hardware technologies. Encouragement, enthusiasm, and excellency is one of the major aspects of the Department of Computer Science. The department started functioning in July 1997, and since then, it offers a 5-year integrated course leading to the degree of MSc in Computer Science. The department also offers a 2-year MSc Computer Science course and PhD program. The department has a very good number of publications in reputed journals, and the department is blessed with several successful alumni who are presently working in reputed positions around the world. With an object of encouraging the spirit of research and innovation, the Department of Computer Science feels proud to host this webinar. Now, to start with the inaugural function, I consider it great honor to request Professor C.R. Bhattacharjee sir, Dean Albert Einstein School of Physical Sciences, for the welcome address. Now, I will hand the microphone over to Professor C.R. Bhattacharjee sir to present his opening remark. Sir, please. Over to you, sir. Professor C.R. Bhattacharjee. Sir? Sir? Dean, sir?
Yeah, hello.
Yes, sir. Yes, sir. Over to you, sir.
Okay, fine. So, a very good morning to one and all. Honorable Vice Chancellor, Professor Dilip Chandranath, esteemed speaker in the webinar, Dr. Shirajul Chaudhuri, Dr. Alok Chakraborty, Dr. Shishendu Das, Mr. Srinivas Kandula, Dr. Amitabh Das, Dr. Manosh Bhattacharjee, and Dr. Pranav Das. And Professor Pankaj Dev Sharma, Head of the Department of Computer Science, Dr. Pradipta Das, the convener of the webinar, all participants and faculties, scholars, and dear students. It gives me immense pleasure to note that a webinar on such a frontier theme is being organized by the department. The concept of big data and application analytics to get significant value from it is a new trend. The big data analytics ensure speed and efficiency. It can influence future decisions, identify insights for immediate decisions. The ability to work faster and stay agile always gives organization a competitive edge. A relatively new technology, cloud computing has revolutionized businesses and their operations, and fast becoming the cornerstone for the digital transformation of companies. The technology leverages virtualization to provide companies to optimize their budget more efficiently with on-demand data storage, computing power, and various other cloud services. A lot of businesses today engaged in digital transformation remain competitive in today's crowded market. The range of applications of quantum computing seems to be limitless. As a student of chemical science, I'm aware that quantum computing enables calculations of the various states of large molecules extremely quickly. These empowers researchers to simulate the interaction between substances and cells much more accurately, leading to development of medicinal drugs. The quantum computing is destined, therefore, to exert a major impact on the healthcare, energy, and logistics sectors. Over the years, the Department of Computer Science has made steady progress and meaningful impact with a band of experienced and young faculties and vibrant group of scholars and students. I deeply compliment you all. I'm certain the deliberations by the experts today will unfold newer horizons for the beginners and enthuse our scholars and young faculties to recognize the potential of these concepts and contribute further. I wish the webinar a great success in generating the much needed interest and triggering young researchers to proceed in these upcoming areas that are predicted to transform the whole of the modern world. Thank you. Wish you all the best. Again, warm welcome from the School of Physical Science to all the participants and the invited speakers. Thank you, Munmi.
Thank you. Thank you very much, sir, for your influential message. I now request Professor Pankaj Kumar Devasarma, sir, Head of the Department, Computer Science, to address the gathering. Over to you, ASOD, sir.
And good morning, everyone. Thank you, Professor C.R. Bhattacharjee, Honorable Dean, A School of Physical Sciences, for your thoughtful and thought-provoking inaugural address. We are very much encouraged from your inaugural address, sir. So, Honorable Vice Chancellor, the patron of this webinar, Honorable Dean, Albert Einstein School of Physical Sciences, respected resource persons, Dr. Shirajul Chaudhuri, Alok Chakraborty, Dr. Shishendu Das, Srinivas Kandula, Anindita Nath, Dr. Pranav Das, Amitabh Nath, and Manosh Bhattacharjee. departmental faculty colleagues, Professor K. Hemachandran, Professor Bipul Sampurkayastha, and Professor Sahinara Begum, and all the other faculty colleagues and organizers of the webinar, and the participants as well as our students and research scholars. So, as head of the department, this is, as well as a faculty of the department, this is a very proud moment of us, not only because we are trying to amalgamate 4 frontier disciplines of computer science into one theme, and at the same time, the resource persons are most of the resource person out of them 5 are former students and alumni of the department. They are working in different spheres and academicians as well as technocrats in different locations of India and abroad. So this is definitely a proud moment for us, and today is that day that we are going to hear from our students, for our former students, about the achievements in the science, in the computer science, about which we have been as a department practicing for the last 25 years. So from the point of view of the webinar, this webinar, as I mentioned, has been trying to amalgamate the theme on the 4 different frontier topics of computer science, though the topics of data mining, which led to big data analytics, has emerged about 35 years ago, and quantum computing too had its basis around in the early 90s. However, it is getting consolidated over all these years. Cloud computing is advanced to such a state that giving wider accessibility and computing capability to the installations worldwide. And all these have become possible because of the advancement of a very efficient hardware at the bottom. That is the hardware technologies and its advancement. That is thanks to our physical sciences and the advancements in electronics engineering. So I welcome all the members in today's webinar. And all these 4 topics, particularly, this can be thought of amalgamation from different contexts, from the viewpoint of data mining and big data analytics because of its true complexity in the form of availability of the data and its form and its structure. Basically, no structure in the data. We need to structure it. So the theme goes into different directions like development of algorithms, storage, accessibility, data availability through various means requires structuring the data, but at the same time, when we talk about big data, particularly, hardly there is any structure which can be assimilated brought into a common platform. So the emphasis is not only on computing but also in representing the data into a particular structure which is conducive for computing, and therefore, not only efficient algorithms are required but also it requires efficient hardware and storage capacity because of the sheer volume of the data. Today we talk about in terms of exabytes, in terms of the availability of the data. Quantum computing began in the early 90s, and it's a very challenging, especially in the absence of hardware equipments, widely non-availability of hardware equipments which can support quantum computing from the scratch. However, the quantum computing algorithms are possible and can be implemented in the existing hardware and leading to much better algorithms in terms of efficiency and computing capability. Cloud computing provides us the accessibility and affordability of resources for data storage as well as computing across a seamless environment in the distributed setup. So all these are required to be supported by adequate hardware technology, hardware equipments, so that the key to computation today is data transmission. And data transmission not in one location, it is across locations, which means an efficient network underneath. So in order to have a data transmission of high speed data transmission, this underneath network has to be strong and efficient, and there requires the extra hardware capability as well as from the computing capability of the processors as well as the GPUs we talk about today. So I hope in the webinar, which is getting into way from now on. We'll deliberate all these issues as well as try to find out a common goal on which all the four topics can have some commonalities as well as have scope for further individual developments. So it is going on endlessly, the developments in the subjects, and we too are trying to becoming part of this global development of the subject as a whole and trying to achieve those solutions of problems for which the world is longing at this moment. So with this, I'd like to welcome all the members and the resource persons, faculty members, and at the same time, I would like to thank you, Professor Siyar Bhattacharya, Honorable Dean of the Science and School of Political Science, for sparing us time for our webinar. Sir, thank you, everyone.
Thank you, sir, for your words of wisdom. I now request Professor K. Hemasundan, sir, Department of Computer Science, to say a few words to the gathering. I will hand over the microphone over to Professor Hemasundan, sir. Sir. Professor K. Hemasundan, over to you, sir. Professor K. Hemasundan, sir.
Munmi,
Yes, sir.
Sir has informed Sir health condition is not good. Sir has joined, but I think he will not talk. His physical conditions are not up to the mark.
Okay, sir. Okay, sir. I now request Professor Vipul Purkasta, sir, Department of Computer Science, to say a few words to the gathering. I'll hand over to Professor Purkasta, sir.
Thank you, Muni.
Yes, sir.
Honorable Vice Chancellor, Professor Dilip Chandranath, our respected Dean, School of Physical Science, Professor C.R. Bhattacharya, our Honorable HOD, Professor P.K. Dev Sharma, my dear colleagues and students. It's give me great satisfaction considering the fact that what we saw as a department now bearing fruits in the context of today's webinar. Most of the resource persons are our past students. It gives us immense pleasure that the students are involved in innovation and teaching in most advanced field like big data, which is becoming synonymous with AI, that is artificial intelligence. The core of which is the fact that we do not learn by following rules. For example, children do not learn walking, talking, etc. by following any rules. It is also very satisfying that our students are contributing in advanced field like big data in both innovation and teaching in different institutes, not only in India, but also of different parts of the world. As far as the webinars are concerned, I hope there will be a webinar also organized to facilitate the expected new normal. As the experts are suggesting, because of the fallout of the pandemic, In this context, it may be mentioned that our Honorable Prime Minister and our Vice President, in addressing different forums, suggested to develop a hybrid model consisting of both offline and online mode in teaching, research, and many other activities as new normal as consequence of the fallout of the pandemic. We must, as a department, endeavor to do that. I wish today's webinar on big data and others related and advanced field a big success. Thank you very much for allowing me to share my thoughts. Thank you.
Thank you. Thank you, sir, for sharing your knowledge with us. I would like to request Professor Sahinara Begum, Madam, Department of Computer Science, to address the audience. Now I'll hand over the microphone over to Madam.
Thank you, Muni. Very good morning to all. I'm given to understand Honorable Vice Chancellor Sir is not present in the meeting. But to begin with, yes, respected Dean Professor C.R. Bhattacharjee, respected Head of the Department, Professor Pankaj Dev Sharma, Professor Bipul Shampu Prestu, all my colleagues, and dear participants, and of course the resource persons who have joined the meet at this point in time. It's an honored privilege for us to host this webinar from the Department of Computer Science, which would cater to the innovative thoughts and a lot of research ideas would come up for the young researchers and the students of the department and other participants from all across. The theme of the webinar is well chosen. It is an apt theme, right from big data, which could be a structured, unstructured data. And of course, as we all know, big data is the fuel. It's the capital of the COVID era. I mean, it was before even, but COVID era has made it even more impactful, more powerful. So big data leading to big data analytics would discover a lot of patterns, and I'm sure a lot of discussion will happen in next couple of technical sessions. And other theme topics on cloud computing to quantum computing to the hardware technology support, that's very well chosen. And just other day I was reading a Google News where Google plans to have a very useful workable quantum computer by 2029. That is a target. So the IT giants are working on this the technology support for the kind of big data analytics which we are wanting to have. So as I feel the digital world which we are into now, the digital was one of the channel of communication, but now in the COVID era, this is the channel, and this platform is generating terabytes of information every moment, and this needs to be captured, processed, and made of good use. So yes, quantum computing would bring us a lot of new computing capabilities, which of course the traditional computers are not able to provide at this point in time. So quantum computing, quantum computers are in the pipeline. And as I said, Google is planning for a very workable quantum computer by 2029. So with this, I feel most of has been said by our respected head of the department. He has very elaborately, presented each of the topic, the theme of the seminar. With this, I would say I would leave the main discussion to the resource persons, and we are delighted to have our own students as resource person. It gives us immense pleasure to be able to invite them. we invite all these resource persons, especially in the first session. I see we have Sirajul Chaudhary, we have Dr. Alok Chakraborty, we have Dr. Shishendu Das. So these are very prominent students of the department. They have been excellent students, and they are now playing a greater role in taking the department forward. So we welcome 3 of these resource persons in this first day of the webinar. Of course, second day also we have good number of sessions, and with this I would really wish all the best to the coordinators who have organized this event, for the research scholars and the students of the department, and every other participant who's joining us for the webinar. With this, I would say the focus is more on the trends, the technology trends in the COVID era. Let the discussions be focused towards how we can leverage this technology in many different aspects of our life, real life scenarios, to the application, different use cases of the COVID era, the technology which you want to venture into. So I wish all the best to the coordinators and the the department. Of course, without the support of the administration, this would not have been possible. We thank the administration. We thank respected Dean, Professor C.R. Bhattacharjee, for extending all support in every endeavor of the department. Thank you all, and thank you for giving me this opportunity. I'm sure I will. I'm planning to attend all the sessions, because I'll be delighted to be on the other side of the table, we say, but then yes, other side of the camera this time. I'll hear from our own students, and that is a joy in itself. So thank you all, and wish you all the best. Thank you, Dr. Pradipto, and other coordinators, Dr. Rakesh and Punendu, for arranging this event for the department. And thank you, Munmi, for letting me say a few words. Yes.
Thank you, ma'am. Your encouraging words always inspire us. May I now request Dr. Pradipto Das sir to address the gathering. Over to Dr. Pradipto Das sir.
Thank you, Munmi. Good morning, all of you. Honorable Vice Chancellor Sir, Professor Dilip Chandra Nath, Honorable Dean, School of Physical Sciences, Professor C.R. Bhattacharjee Sir, Honorable Head of the Department of Computer Science, Assam University, Professor P.K. Dev Sharma, our respected teachers, Professor K. Hemachandran Sir, Professor Vipul Shankar Sir, Professor Shahinara Begum Ma'am, and other colleagues, my dear students, scholars, and all the participants, those who have joined in our webinar. And I would like to welcome all the resource persons, those who are basically our friends or colleagues, and I welcome all of them in today's webinar. And as coordinator of this webinar, I am just giving some statistics of this webinar. In our webinar, we have received application from participants. Total application we have received 192 numbers, and we have confirmed 100 plus. That means around 105 participants, and out of 105 participants, almost 70 participants, they have confirmed their participation. And in the meeting now it's 66, including all the officials. So it's a good number, and gradually maybe in the technical session the number will increase. So with that hope, we are actually starting our today's webinar. I think the webinar will be very rich in content, and people will get different kinds of knowledge from all those latest topics which we have kept for our webinar. And that is our intention. And actually another objective is to give a platform to all the alumni members, pass out students, those who are flourished in different fields. That is also another objective of this webinar. So I wish all the participants, I thank all the people present here today in this online meet. So over to Munni. Thank you.
Thank you, sir, for your influential message. May I now request Dr. Punendu Das sir to say a few words to the audience. Over to Dr. Punendu Das sir. Dr. Punendu Das sir.
Okay, thank you, Munni. A very good morning to all of you. Respected Professor C.R. Bhattacharya, Dean School of Physical Science. Respected Head of our department, Professor Pankaj Kumar Devasharma, Professor Sahinara Begum, Professor K. Hemachandran, Professor Bipul Sam Purkaisto, all the faculty members of Assam University and other institutions, research scholars of Assam University, students, and my dear participants. First of all, I thanks to our Honorable Dean, School of Physical Science, Professor C.R. Bhattacharya, sir, for his inaugural address in this webinar series. Despite his busy schedule, he always give us time whenever we need. As a faculty member of School of Physical Science, Assam University, I want to mention that we get Professor C.R. Bhattacharya sir guidance whenever we need. Whenever we ask, he always give us fruitful guidance. And I believe that our participants will be motivated from his inspirational lecture. I also thanks to all our resource persons from who most of them are our alumni of our department. I am very much thankful to all of them. I also thanks to all our research scholars. As a coordinator as one of the coordinator, I want to mention that we are able to doing this webinar series due to our scholars. They are the backbone of our department. I am very much thankful to all of them. I also welcome to all the participants, and I hope that they will learn something from this webinar. I request them all to participate in all the sessions sincerely, as all our speakers are very much well-established people in their own field. Many of them published many research papers in well-established journals and many technological firms also. They are well-established position. They have well-established working as a well-established position in many technical firms also. I hope that our dear participants will learn many things from our resource persons. I request you all to participate in the program sincerely. I do not want to. This is already we are late. It's time to start our technical session. So I conclude my lecture, and I thanks to all of our resource persons, our students, our scholars, and all who are presenting here. Thank you.
Thank you, sir, for your encouraging words. May I now request Dr. Rakesh Kumar, sir, Department of Computer Science, to address the gathering.
Thanks, Munvi.
Over to Dr. Rakesh Kumar, sir. Yes, sir.
So thanks, Munvi. Good morning to all. Honorable, respected C.R. Bhattacharya, Dean School of Physical Sciences, respected Head of the Department Computer Science, Pankaj Kumar Devasharma, and Professor K. Hemachandran, Professor Vipul Sam Purkaisto, and Professor Shahinara Begum, and our respected colleagues. Greetings to one and all. It gives me immense warmth and great pleasure to grace all of your presence in the interest of the entire committee. Before we begin this webinar, I would like to express my heartfelt gratitude to all of you who sincerely committed to this event to make it a success. This event would have been impossible without the support of each and everyone present here. Webinars are organized and conducted for the general audience to gain insight and information that would remain effective in their life, exercise, and work. With these words, I conclude, and thanks to all. Thank you. Over to Munvi.
Thank you, sir, for sharing knowledge with us. May I now request Dr. Pradipta Das, sir, to propose the vote of thanks. Over to Dr. Pradipta Das, sir.
Thank you, Munmi, because we are running late. So, in the boot of thanks, I would like to thank Assam University Administration for providing all these facilities to organize this today's webinar. And I would like to thank our Dean Office as well as our departmental office, HOD, Office of the Head of the Department. They have provided us all the facilities to organize this event. And since it is a teamwork, we all the faculty, young faculties of the department and scholars of the department, we are actually jointly doing the work for this webinar. So I would not say thank for them, but it's a teamwork. So that's all, Munmi.
Yes, sir. Yes, sir. Thank you, sir. As we are running late of time, so we would conclude our inaugural session, and now it's time to start our first special session by our invited speaker, Mr. S.I. Chaudhary from USA. He will be discussing on career progress, data science, and data warehouse. Dr. Sanju Das, sir, from Department of Computer Science, is the coordinator of the session, and he will be moderating this session. For your information, if you need to post any comment, kindly utilize the chat window and we transfer them to the respective panel during the session. So we have the profile of Mr. Sirajul Chaudhary. Read his profile. Chaudhary is a data analytic professional with expertise in various processes, data analysis and extensive in implementation of data warehousing projects from scratch, improving scalability and performance of existing data warehouses. He is well versed in data architecture, data governance concept, and Six Sigma methodologies. He has completed his master's from our department itself, and now currently he is working as a Scrum Master in Bank of America. His work experience include a senior project manager in Syncron Technologies, and he was a project scientist in IIT Guwahati also. He has a good number of published work in reputed journals and conferences, and his skills include data warehouse, data analytics, data architecture, language like Python, C, C++, and so on. So we rarely get this kind of opportunity to listen to the word of successful alumni like Mr. S.I. Chaudhary. So let us have the privilege of listening to him. So I'll hand over the microphone to Mr. S.I. Chaudhary to present his talk. Over to you, Mr. S.I. Chaudhary.
Thank you very much for the warm welcome, and I would like to thanks everyone, especially coordinator Pradipto Das and Sanju Das for giving me a chance to speak to all of us. Just before I begin, is my microphone it's audible to everyone? It's
Yes,
clear
yes.
enough?
It's clear.
Perfectly. It is working perfectly, sir. You can start, sir.
Okay. All right. Thank you. And yeah, very good to see my Madam Sainra Begum after a long time. And yeah, and I haven't seen Bipul sir, but I will see soon. So yeah, it's tremendous happiness. So maybe you might have seen it from my face. Yeah, that's pretty much it. Maybe I think we can start. I have quickly created a small presentation so that I can go through in this webinar. So I will start sharing it, and then probably we can take it from there. So. Probably Munmi, is it my screen is visible?
Yes, sir.
Is my okay? The screen share is visible to you.
Yes, sir. Yes.
Right. So today we'll be mainly talking about data, right? I mean, data analytics and the data warehouse. Mainly, I mean, we deal with a lot of data. So how it works in the industry side of it. So that's the main topic that I'll be discussing, where we are leading to. So yeah, as we see, I mean, this is a word cloud. You see, when we when we say data, it is a very four-letter word, but it has a lot of immense presence all over, right? I mean, as Saindra Madam was rightly said, the future and terabytes of data, it's being generated every day and every seconds, right? So I mean, what all it is, right? What is analytics? What is data, and what all related, right? So, whenever we say data, these days, it's quite everyone heard about is data science, right? Data warehouse, data analytics, statistics, mathematics, right? Fraud detection, all this comes in data, right? It's so if we quickly see what data analytics is means, right? So data analytics revolves around mainly three or four. I mean,
Sir, Mr.
sorry.
S.I. Chaudhary, sir, your presentation is not visible, sir. Sorry to interrupt. It's not visible,
Oh,
sir.
okay.
Kindly check once. Yes.
Sorry, that's entire session. So, is it visible now?
Sir, no.
No. Stop sharing. Okay, I think it's coming up now.
Yes, sir, now it's coming.
You can see now.
No, sir, not clearly, sir. Only the window is coming, sir.
PPT is not coming. You switch over to
Yes,
PPT.
sir. The whole window is coming, but your PPT is not coming.
Yeah, just PPT. Point is so open window application. Sorry. Is it now? No?
Yes,
Yes,
yes.
yes.
Yeah, sorry about that. I thought it's visible. So yeah, so we are talking about data analytics, right? I mean, and basically where we are leading to all this related to data. So that's a quick presentation that I have created for this particular webinar. I was saying when we talk about data, it often comes data science, data analytics, data warehousing, right? And all the related stuff, right? We have mathematics, we have statistics. It's all combined, right? I mean, it's not like, oh, we are in data computer science, they're in physics, or they're in math. It's not like that nowadays. Right? It's all like totally mixed up. So when we say data analytics, what actually it refers, I mean, or what actually brought, right? So we the data is coming in from different source of data. We have every day we have lots of data is in the internet. Hello, sorry.
Hello, sir. Sir, your voice is also not clear. Maybe microphone has some problem. So kindly check, sir.
Hello, is it better now?
Yes, sir. Your voice not clear. Maybe there is a problem in the microphone, sir.
Is it clear?
Names are not
Munmi,
yes, ma'am.
this is Madam speaking here. I think there is some network congestion. Sirajul, if you could put off your video and just use your audio and the presentation.
Yes,
Oh,
yes.
okay.
There is some network congestion. Please put off your video and just use your audio and the presentation.
Let's see. Let's try. Thank you. Is it better now, or it's the?
Yes, it is better now. Yes. Now your voice is
Okay.
clear. Yeah.
Right. Thank you. So data collection and integration, and we have data visualization and reporting, right? And whatever the data coming in, what all data quality assess and improvement, right? And the enterprise analytics solutions, right? So these are main four wide category that I would say, like which revolves around data analytics, right? So let's see what data collection or where it leads to, right? I mean, what is the data integration? So if we see data warehouse is thing, but it deals a lot of data sets, right? So we have for any company or organizations, there are a lot of internal systems, right? And then we have external sources. So like in the internal system, we have mainframe data sets coming up. We have from data from Oracles or some flood file systems or Excel data sets or CSVs or text files, right? All these data, for someone to view in a report or something, then that has to be massaged properly, right? And then and then it has to be stored somewhere. So that's where the ETL comes into picture. That's mainly the extract, transform, and load. Stands for ETL stands for. So all the data massaging and cleaning and also kind of aggregation or I mean ordering, all those happens there in that area. There are external sources as well, like you're getting your prices, your Bloomberg data, right? All this, if you see it from the financial sector, right? So all those loads into a database. Actually, it's not whenever we say data warehouse, it's a big database where we store all this data, right? I mean, and then we have by the subject or we streamline into more smaller part, like this is contingent finance or human resource or all the transaction based data sets. So we have smaller data mart, and then we have this different frames, right? All this data where it goes to, right? We have this it goes to reporting side and some data analytics, like when it's data analytics, the data science and all this data related research and investigations comes into picture here, and again data mining, right? So these are you would say some of the downstreams of consumers of the data, right? So that's a very big picture of data warehouse. Right, and let's move on to the topic, right, data science. So what actually is the data science? So data science is nothing but that deals with data that everyone aware by this now, right? And it's a interdisciplinary field, as I mentioned. Like it has many different methods people are using. It's still in it's a rudimentary stage, I would say. I mean, it's not like very matured. People are trying different stuff, right? So many processes, algorithms are being used, right? Almost everything that has something to do with data. I mean, that's basically as simple as that, right? And for that, we have the collecting, analyzing, modeling. So when we say collecting, data warehouse, and all this comes into picture, right? All these data analytics, analyzing, right? And the modeling for any machine translation and all those related. So data science is nothing but related to mining, data mining, and machine learning. That's where it is driving to, right? Deals with both structured and unstructured data for the insights. So when we say structured, it's like we have the database and all these structured SQL and all the RDBMS and all those, right? And unstructured, like when I mentioned the flat files and all those, right? So they don't have any structures, like you have some data set from the from some internet website. It may be in any form, right? So those are unstructured. So that deals with data science, deal with all these types of data. Just the pictorial representation, how what are the components data science relates to. For example, right, machine learning is a very integral part of data science. Business analytics and artificial intelligence, that comes generally with deep learning, right? Data science, data will always be there. Without data, there won't be any data science or analytics. Software development, of course, will be there. There's big data, yeah, definitely, right? And statistics and mathematics, the backbone of the, I would say, one of the backbone of the data science, right? So moving on. how a brief history behind how this data science comes up, right? So before data science, data mining was very popular, very common, right? I mean, it was mainly for many of the researchers were doing research on this data mining stuff, right? Mainly that mining itself, if you infer, it's something to get some useful info from the data, right? And say back in 2001, this scientist William S. Cleveland, right, gave data mining to another level, where what he does is he does the computer science algorithms, whatever technologies with the data mining, right? Basically, all the heavy usage of the technical statistics, right, which made the data mining to another level, which now we vaguely known as a computer science or the data science. Sorry. And one of the main reasons which ignited, I would say, is like towards the data science is the emergence of the big data or emergence of the web, internet or web, which created an enormous, gigantic amount of data in our daily life, right? That eventually forms the big data, and which immensely help towards the all this analysis related to data science, right? And of course, rise of big data sparked the rise of data science. And so, if you, I mean, from the just layman or from general perspective, if you see where are the data sciences being applied in this daily life, right, in the different domains. So we have finance and banking. There we have risk analytics, right? Some clients' profitability, right? Fraud detection, and so on. Then in retail, again, we have this customer identification, product recommendation, analyzing reviews. So when we say retail, e-commerce, this Amazon or Flipkart or Alibaba, this all this comes, right? And have you ever imagined how, I mean, when we search for a particular product in the next day or few days, we keep getting some emails like there's some discount here, this is better review and all those. So they're tracking each and every move of a customer, right? And then do some analysis. Oh, this customer is wants to buy this kind of product, this customer is actually that kind of things, right? All these suggestions or anything like product recommendation is happening there. When in healthcare, we have some image analysis. So before we used to do say OCR, right, optical character recognition and all those image related stuff, right? So here we have in the deal we have different type of images, right? That's also is being used, right? Drug discovery, visual assistance, you name it, any field, right? In manufacturing, insurance, transport. Like in transport, we have self-driving. How is it possible? Right? And in the even though it's not completely self-driving, if you see the cars like 10 years back and now, we have a completely different features that are available, right? I mean, automatic, uh, accidental from the accidental more secure way of and how it automatically stops and although there are a lot of programs inside, right? The monitoring system. So in every, I would say data science is used these days in every field. At least people are trying to, even though there are full-fledged applications in the market might be very less, but they're everywhere. People are trying investing in this particular stream of science. So now I would like to overview in the banking and finance as I'm more of in banking field. So now mainly risk modeling is one of the area where heavily these industries invest on, right? Basically, whenever a particular this customer borrows some loans, whether he will be able to pay it back or not, whether it will, I mean, will become a defaulter. So all this you can study, I mean, based on the history of his transactions and also that is one of the main area for the banking and also fraud detection is also comes another important area where I mean, every day we, because of the increase or rise in online transactions, we are it's very easy for us to become a victim of this thing, right? So that's where I mean, fraud detection comes into picture. I mean, based on all those analysis, right? They can detect those things, and then predictive analysis and so.
Sir, your voice is not clear. Sir. Again, there is some microphone problem, sir. from your end.
Sorry. Looks like I'm connected to the.
It's maybe,
Hello?
yes, sir.
Is it better?
Sir, little better,
No?
but still, yeah. Yes, sir. It's not coming properly.
Let me switch my internet. Let's see. Audible now?
Yes, sir.
Is it audible? Is it
Yes.
proper? And all those can also be predict based on the historical data, because as I said, data warehouse is kind of a warehouse where we dump all the data, and it lies for years of data. Based on the data retention policies, it will be there forever. I mean, until we archive it to somewhere else. So it was a very good platform for scientists to do all these kinds of analysis and predict. So data science at Bank of America. So as I associated to Bank of America, I thought better I will just put some insights into what is going on here. So Erica is a kind of one virtual assistant. It's already live. I think it was put on live on 2018 or somewhere 2019. So that's a virtual assistant that uses again natural language processing. So that's again comes under AI, right? And also leverage various the machine learning and the predictive analysis algorithms. Again, lending and loans, it like that, person or a customer is defaulting to loans, or he was able to about the study about his credits. Capital markets, news analysis, right? For example, news analysis, there are various news about the organization or their customers related, very high profile customers. They have, so they need to study their news, whether it will impact their reputation or financial loss. All those kinds of analysis was also being done. I mean, that's some initiative going on. And I also took another example, for the JP Morgan, as it's one of the largest financial investment bank. So many people do many stuff these days, right? So as we say, data scientists can do a lot of stuff, right? But if you see deeply inside, right? So starting from the data collection might be related to structure, unstructured, right? All this data. So mainly the software engineers like us, they deal with ETL and all those technologies that are available in the market. They do all this and build a data warehouse or put it in some kind of data store where they can utilize for any analysis. Correct. And then see if once data is collected, so we have to store and organize. So still is a kind of both related, right? Data collection, storage, organize. So in some firms, in some companies, probably one person, they might be, all the data engineers might be doing it, all the parts, right? But in some more matured firm, more organized companies, some they might assign only some few engineers, software engineers to collect to build all this. Some storage, organize, some other designated data engineers might be doing it. All the data is there. We have analyzed and this. So learn and optimize actually it refers to the machine learning side of it. Like once we have the data, now analysis can begin, right? All the data, how it's predicted and all this stuff. So there are some data science analysts. I mean, it's just a term that people use in some of the firms, right? And then at the top we have this AI, where deep learning, unsupervised learning, all this stuff is again handled by these research scientists and is backed by the ML engineers. So whenever research scientists or data science coordinator, they need to deal with machine learning algorithms and all. So machine learning engineers are coming to picture there. So that's the hierarchical needs, I say, where in the industry these days. So moving on, important skills for data scientists. So as a data scientist, what important skills that one have? As I said, the mathematics, statistics, on points that I mean, it's like just learning about Python or R or just whatever language is available in the market is not enough, right? So you need to have more on the statistics, many technical statistics and mathematical backgrounds, ability to understand the analytical functions, right? Data visualization, what the data is there, what is the trend, and all those. There are various libraries and tools available, so people use that. And then, of course, with experience with some SQL part, if we have to deal with a database side, right? Data wrangling is nothing but how to, I mean, so if you see cleaning and all those data cleaning, data massaging, that piece is also come into picture. So it's a very broad term, and a data scientist has a lot of, this is important skills that he must have to prosper in his field, right? And when we say data science, machine learning is an important concept, right? That's where all the analysis, predictive analysis, extracting data from this unstructured data set, and those are being used in the machine learning piece, right? So there are some of these are technical side of it. I mean, those who are technical, maybe they must be using it or somewhere, or they must aware about it. So scikit-learn is one of the famous open source library developed in Python, right? Mainly it is for analyzing the data and classification and feature selection, all this, and also it has some features capability to do some data mining, right? And the TK again for this for natural language processing. When we say natural language processing, it comes out mainly the stemming, lattice, and tokenization. All this comes into picture, right? Where a word has to we have to bring it to the root form, and then from that with various meanings, right? So that all those libraries are again in Python. So PyTorch is there, Keras, Apache Spark is again another platform where big data and also it's a very comprehensive data science tool that people use, right? And SAS, MLR is a package is in language called R, right? So not aware about this language, but a lot of people use in the data science or machine learning area, right? XGBoost, Shogun is written in C++. So these are some of the tools that that people are using it, and in the market, most of them are open source. Anyone can download it and use it for their research or any any work or learning or anything, right? So now, yeah, it's just so we have talked about many stuff like what will be the future, right? Future of Yeah, future is as I said. I mean, it's one of the thing is like we don't have clearer roles, responsibilities as of now. Like many people are doing many stuff. Some data scientists involved in some companies starting from the scratch, like collections, the integration, all the way to this deep learning. But in some cases, he must be defined to some writing some algorithms or regression, some of the classification algorithms, right? So say in the long run there will be more more defined roles and responsibilities, I would say. I mean, that's many predict, right? And so data explosion, data is every day we have lots of data, lots of gigabytes of data is there. So basically that in turns will I mean will kick off all the data science rise of the automations because of the data, right? And one thing is that either scarcity or abundance of data scientists. This is because many people today is very I mean keen on learning data science, right? Either they're in the some of the universities, they already they have this PG diploma or full-time MS course in data science. And then many of people like us who was using in data analytics, and also they want to upgrade their skills. There are so many online resources. People jump in and start learning it. There will be a lot of I mean abundance in one term. But as I said, data science is not one particular specific domain, right? It revolves around many other stuff. So learning all this stuff to master of all this, it's not possible as a human, right? I mean, only few who has inborn qualities probably they can have. But so I mean, there will be definitely for anyone who learn all these machine learning technologies, there will be a lot of place in every organization, starting from e-commerce, manufacturing, or auto industry. Everywhere there will be need of the data scientists or data science related professionals. Uh, yeah, so that's all actually I have. I mean, that's I think we are 10 minutes over. So
Yes, sir.
yeah, and some of the references and any questions or anything.
If the participants have any question, ask Mr. Siraj.
Okay, if anybody doesn't have any question, thanks a lot for giving me this opportunity, to Pradipta and Sanjudas, and also to their respected teachers, vice chancellors, who taught me and brought me at this level. I'm always grateful to my respected teachers. From this is from my heart, I'm saying, and yeah, thank you so much, everyone, my dear friends and young ones. Yeah, thank you.
Uh, Thank you, Shirajulda, for giving us the time in spite of your busy schedule. And our social coordinator, Sanjudas, is also present here. And let me inform the participants, Mr. Shirajul Chaudhary, who is the first batch student of Department of Computer Science. And their session was 1997 to 2002. Sanjuda and Sirajul Chaudhary, both are actually batchmates. And we are very much grateful that today one of our alumni members from the first batch has joined in the webinar as resource person. Basically, our webinar topic is big data, cloud computing. So his deliberations will definitely benefit us. All the participants will definitely enlighten from your speech. So thank you very much, Shirajulda, for giving us time. Please keep in touch with the department, all the faculty members, your younger students, brothers and sisters of the department, so that they will get some inspiration from you people. So thank you so much.
Yeah, thank you, Pradipta, for giving me this platform. And happily, I mean, if anything comes up, definitely I would like to be part of it. Yeah, thank you so much. So I will sign off. I have some other activities or my work related. So I will sign off, everyone. So thank you. Have a good day.
Thank you. Thank you.
Thank you.
Thank you, sir. It will be a great pleasure for us to listen to you again in our future event. We just now ended our first special session, and now we have our next technical session 1 by Dr. Alok Chakraborty, Assistant Professor, Department of Computer Science and Engineering, NIT Meghalaya. He will be discussing on quantum computation.
So, a very good morning to one and all. I convey my respects to my teachers in Assam University who are present in the meeting, and I also convey my respects to my seniors. So today we will be talking on an interesting topic. So it's about quantum and the current software and hardware support in the industry. So let me try to share the screen. Do I have the share rights? Okay.
Yes, sir. So can you please make it full screen?
Yeah, it is full screen.
Yes, sir. It is here. Yes.
So content topics and problems in current software and hardware support. We started around 1050. Yeah. So and computing as a quantum computing was considered kind of quite theoretical. And yeah, it's not rocket science, but it was the notion till 2016. Okay, so as it's mentioned here, that till 2016 the notion was that quantum computing won't be realized. Okay, but later the hype came, okay, when like there were promises made by different organizations like IBM, Microsoft, Google, like that. So then like there are so many news articles because there are so much funding by different governments, okay, organizations, okay, that everybody start thinking that quantum computing solve any problem. So let me tell you, this is a big no. So it's not like that. Okay, and we'll see the justification later from a computer science perspective. So how can we understand quantum computing then? So quantum computing can be seen as a promise. It's a promise that when commercial quantum computers will be available, because right now see we have the commercialization with the current conventional computers, but the quantum computers are still in the experimental stage. And what do I say? We are currently in the NISC era. That also I'll be discussing later. So if they will be available, then it will be possible. By tough problem, I mean the problems which cannot be solved in polynomial time. Okay, and they are like falling either in the class of NP intermediate, NP, and something like that. Okay, in the P space. So with the current high performance computing systems, the best ones, okay, that we have available on the planet, whatever speed we are achieving for problems, say for example, the problem is a acceleration problem. So such kind of problems can be solved with availability of commercial quantum computers. That's what is being expected. So basically, about computers, if I have to say, I can say that there are 4 types of computers. Okay, so we had these analog computers, right, in the early days. So where the information would be processed in terms of electrical current, and processing will be analog and things like that. Okay, so the digital technology was taking shape, and later on the processing of information, okay, started with the processing of representation of numbers in terms of bits. Okay, we know that it's a binary number system mechanism for number representation, and all the computers that we are using, okay, in the present days, okay, is following the digital processing of information. So we had analog computers, we had digital computers. We also have realized, okay, highly performing parallel and distributed computers, right? So parallelism can be achieved via using several, parallel processors, GPUs, and things like that, or we can connect different computing elements, okay, over high-speed, okay, network, and that way also we can achieve, okay, higher performance, parallelism, okay, and higher computing power. Quantum computing in comparison to analog, digital, parallel, and distributed, that will be coming next. Now, is there a problem with current computers? We already have highly powerful computers. Okay, yes, there is. So current computers are already powerful, but facing 2 barriers. They're facing 2 barriers, and we know that there is a Moore's rule that is with respect to the count of the transistors that gets into the chips, okay, for microprocessing, okay, inside the CPU box. So with the passage of years, okay, and different generations of computers, now we are in a state that we are coming down to almost atomic scale. I think it's close to 10 to 100 times, okay, of the size of a single atom. So this is the situation, and following the trend of increasing the number of transistors in the this microprocessing IC, we cannot continue with increasing more computing power, more speed, and things like that. Okay, so we have reached a summit limit, and as a result of this, the second big problem that is coming is energy consumption. Okay, there's so much of heat being generated. You can see the modern processors, they generate even your smartphones, okay, they get heated up. And if we take some support from physics, then we understand that there is a Lorentz law that tells that there is loss of information when there is loss of energy from a system doing computation in the form of heat and other manners like that. So the conventional computing is also highly energy consuming, and as well as it is like not reversible. This is another phenomenon regarding quantum computing. Quantum computers in current state can act as co-processors, and with the already available prototypes for quantum computing by different organizations like IBM, RBCQH, and things like that. So it has been experimented that quantum computers can be used computing support to our conventional microprocessors that we have inside the CPU box. Like inside the CPU box, we use our microprocessors from say AMD or Intel and things like that. And side by side for gaining more computing power, we also use GPUs, okay, and things like that. Okay, there are different things. So if we take it deviantly, then can't we use quantum computing support, okay, along with the conventional this microprocessors, okay, to gain more computing power. So that's another trend that is ongoing right now. So this is about historical perspective of quantum computing. So the 1980s, so the introduction of this basic model for quantum computing by R. Feynman. So this was discovery phase, and some decade later, the famous quantum computing algorithm was introduced by Short. So as Feynman introduced a possibility or shared knowledge that we can do information processing by harnessing the quantum mechanical phenomena, okay, of matter, and that will give added advantage. And think this Shaw in 1994 showed that if quantum mechanical phenomena can be realized for information processing, then factorization of very large numbers, which are the key to modern information security for these cryptographic algorithms like RSA, okay, and ECC. So that can be breakable, okay, by by being able to factorize large numbers, okay, quite fast, because we know that the root difficulty for the breaking of the current cryptographic systems, okay, by which all these monetary transactions, fund transfers, and different things occur, is basically the difficulty in factorizing the prime product, okay, for algorithms like RSA. So these are like products of huge numbers. Each number is 1024 bits in size or 500 bits in size. Even the typical transactions that we do for online shopping, especially during these pandemic days, okay. So there, every number is, okay, I think at least 256 bit. Okay, that means one number needs 256 bits to be represented. Now imagine, okay, if we like have stronger security by using larger numbers, which need 512 bits or 1024 bit. So these large prime number products, okay, basically for RSA algorithm, we use two prime numbers, multiply them, and the eavesdroppers, they have to factorize the product of two prime numbers so that they can hack, okay, the information, okay, passage or the information channel, okay, to do something. So Short showed that using quantum computation, factorization of large numbers will become easier. Okay. Similarly, in 1996, Grover introduced another interesting algorithm based on quantum computation. So that was another interesting what will be phenomenon, okay. So if we have something more than quantity quick, then it is even faster. Okay. So with respect to the current search speed for unstructured databases, here kind of collection data, okay, and I'll later on say something that we need to do search for so many typical quantum computing typical computing problems, and what is the benefit if you do quantum computation, okay. So those things are discussed. Now this is the most significant, okay, part of the history of quantum computing. Right now we are in the noisy intermediate scale quantum computing era. So every word has a meaning here, okay. So noisy means what? That we have to understand first of all that when we are talking of you harnessing quantum with matter in the atomic scale, and that means what? That at the atomic level, the normal Newtonian laws and other physical laws, okay, do not apply. We have quantum laws, okay, which are quite weird. Okay, so for example, take the example Heisenberg uncertainty principle. So you cannot measure the position and momentum of electron, okay, simultaneously. If you do one, you will have some error in the other's measurement. Okay, so because the electrons are continuously moving like that. Okay, so the current hardware that have been hardware platforms that have been introduced, so they are suffering from noises. When you do computation, okay, so those we like witness noise in quantum computation, and that aspect of this presentation is also to discuss problems. So if you can tackle the problem of noise in quantum computing, then again you gain, okay, much in advancing quantum computing. So in 2016, IBM introduced its hardware support, and you can see, okay, right now there are like several prototypical IBM quantum computers, actual real computers. Okay, they are not simulatory the systems, so they are real computers. Okay, whereas for Petals, okay, it's still not introduced. So there are different like machines. Some are 5 qubit in size, some are like 12 qubit, 15 qubit, like that. So in 2017, Atos introduced quantum learning machine. Okay, so it's a simulation-based system. Okay, but okay, in this system by Atos, it's another company organization, we can run several quantum algorithms. Okay, so there were like many other quantum computing platforms, okay, hardware platforms that were introduced to the world by the organizations also like Google, and we understood that like Google sometimes back advised, okay, news that they have achieved quantum supremacy. So that is another thing, what's quantum supremacy. So if we can solve through quantum computation some hard problem which fall beyond the P complexity class in reasonable amount of time, okay, then that machine, which is a quantum computing machine, achieves quantum supremacy. So there are other organizations also which have introduced their quantum hardware and like prototypical simulation-based platforms from 2016 onwards to 2021. So it's just within 5 years, and all the like hardware support that are being made available, they fall under the NISQ era, because every platform is suffering from noise. Okay? And intermediate means that the bit architecture is not so big. Like for current supercomputers, the bit architecture is 256 bit. Some have 128 bit. Our machines that we are using currently are 64 bit. Okay, and there are some other systems still in use which are 32 bit. they have a short coherence time. I'll explain that later. So that's why what happens is that the number of bits with which we can do processing in these quantum machines, okay, is not too big now. This number of qubits, sorry, is small now. Okay, so intermediate scale, and quantum is quantum computing platform, and we expect that by 2023, okay, in this new scale only, we will be able to do better realization of physical qubits. Okay, and just like we have physical bits. These physical bits can be realized. Okay, I remember way back in 2003, we studied digital electronics. So like we read that using flip flops we can realize a bit. So we can store either 0 or 1, or using this magnetic. Okay, there were two diagrams for the RAM. Okay, for 4+3 size RAM. So one using flip flop, another using magnetic cores. Okay, so we have magnetic core memory. So using magnetic physical phenomena, we can realize a bit which can store only 2 values. But here comes the interesting point: qubits can store multiple values in superposition. Okay? So by 2023, we assume we expect that we can achieve better realization of qubits, and we'll have more control over the noise issue. And there, as a result, there will be more commercialization of quantum computing platforms. And Atos, this organization is thinking of introducing its actual real quantum computing system. Now, as I promised, so courtesy of Atos, this diagram very nicely explains the quantum computing to classical or conventional computing. Am I audible?
Yes, sir.
Okay. So here, what we see that the complexity is increasing. So this is the space and we have that for in the polynomial time table, okay, class, and HPC is anything to parallelism then within fraction of minutes, okay, fraction of seconds to minutes, okay, but in a reasonably short amount of time, which may for some problem we may like afford to give some days also, but we can compute. But imagine if I give an example of factoring a number that's a product of 2 prime numbers each represented using 104 bits, that would take millions of years. So that problem will not fall in the P category. But any problem that falls in the P category, all our classical computers can efficiently solve them. We have efficient algorithms also. And then we have this NP intermediate NP, NP complete classes. So these problems are hardest problems. And we know, for example, Turing 6% problem. If we scale up with the number of cities, it becomes immensely hard to solve the TSP problem. Combinatorial explosion. There are so many problems, which when we increase the problem size n, to a little bigger number, so they drastically suffer for combinatorial explosion, and we cannot solve it. Say if I take chess, okay. So for chess, there are so many options, and no single computer program is available on the planet, okay, that can evaluate all possible moves, okay, for every possible move chance in the game of chance, and tell out the best move. If you can do that, okay, so then we can have a very exceptional chess playing program that will always defeat the grandmasters, okay, but we cannot using the winning power explore all the moves for all possible situations and cases, right? So such problem is called beyond the P class. So as I said earlier, quantum computers cannot solve every problem in a blink of an eye. So it's not that because now we will have quantum computers in the near future, possibly, so we can solve all NP problems. So we can see this outer circle DQB. Okay, so this is for quantum computers. Okay, that is quantum computers can solve some of the NP problems. Okay, not all. And then we have part of the problems NP computers like that. So this clearly explains. Now talking about fundamental biology. So quantum circuits use the principles of quantum theory, such as superposition and entanglement. So as I say, superposition is what? That when we say that a bit stores either 0 or 1, that means we say that, okay, if we have set a bit to 0, it will remain 0 throughout, okay. The memory device has to maintain the bit value to 0 only. Suppose in a pen drive, you are storing data, which is stored in terms of bits, okay, like in the ultimate issue. So 0 will remain 0 for a bit, okay, that means a bit with value 0 will remain with that value. And it's 1, it's 1. There are 2 values only. But in case of qubit is a quantum counterpart for a bit, that means 1 bit, okay. Every bit can store a superposition of 0 and 1. That means if suppose I toss a coin, as long as the coin is whirling, circling in the air, right? We can say that the coin is in a superposition, or you can say linear combination of both head and tail. So what is the final outcome of the toss? As long as coin is whirling in the air, so it's both head and tail are different degrees of head and tail. It's like that. So let us use an equation. Using just one qubit, we cannot just deal with 2 values only, but so many values. Theoretically, just like if I before telling this statement, if I say that how many values are there between 0 to 360 degree, there are infinite values. Theoretically, a qubit can store infinite combinations of 0 and 1. That means some degree of 0 plus some degree of 1. That is the superposition. So that's what makes quantum computing very interesting. As I said, that I will tell or put more light of the deviating trend of quantum computing from analog or digital or parallel and digital computing. So that's superposition. Entanglement is another peculiar physical phenomenon which Einstein said as spooky action at a distance. What is entanglement? That if you measure a qubit's value, which is somehow entangled with another qubit, then the measurement of this qubit will give you the measurement of another qubit. Okay, because these two are entangled, even if the qubits are separated by physical distance, their value will remain same. It's a it's not metaphysical, hypothetical. Experiments have been conducted and shown that qubits have been kept apart, okay, from 7 meters to even kilometers, and like entanglement, okay, times are tracked. So by this, some teleportation experiments are also done and things like that. But at least within several meters distance, 2 qubits can be entangled within a quantum computing system only. Okay, they are controlled pressure. So that is also this key for measurement of like information when we do quantum computation, disentanglement. Okay, so these are the primary like mechanisms for performing quantum computation. Okay, and obviously we need circuits. So for conventional computing, design conventional circuits using flip-flops, okay, gates and or not and universal gates, things like that. Similarly, for doing quantum computation, okay, we have to design quantum circuits. Okay, the quantum computers outperform classical computers using laws of quantum mechanical physics. This I'll just skip because I already told. The basic quantum information unit is qubit, a qubit, quantum. These are different nomenclatures for the information unit for quantum computation. Then this is a very important problem. Okay, this is one of the fundamental problems that every quantum system, most of the quantum systems that are being introduced is facing. This nearest neighbor qubit interaction. So this is a important prevent errors in quantum computation. As I said earlier regarding noisy. So what happens is that because we are talking of atomic scales, so when we are representing qubits using ions, okay, or using photons and conducting atoms, things like that. So what happens is that for interaction of two qubits, okay, for information processing, they must be within a minimum threshold distance. Okay, don't think about entanglement now. That's a different phenomenon that is specially done for measurement of the state or value of a qubit. But when two qubits have to interact, okay, then what? They have to be brought close to each other. Okay? Whereas if suppose you have to process 2 bits, so you can just use wires connect and things like that. Qubits are not like wires and things like that. Okay, so they are like in the atomic scale. So 2 bit values have no question of like interfering each other or things like that. Okay, so we just supply current, so -5 volt, +5 volt. So it's all electrical magic display in conventional computers. But the quantum computers use qubits which are represented in a different manner, and when they have to interact, they should come within a certain threshold distance. The property of operating on only neighboring qubits in implementations of quantum circuits, okay, due to architectural limitations, because all the quantum computers that have been introduced till now, they have different kinds of physical architectural limitations related to matter, because at the atomic scale, they're all peculiar physical laws acting. Okay, so then this this particular important problem, and research can be done on that, is termed as the near-singular property. In order to swap, now one solution that I'm immediately telling about this problem is we can use swap gates. So because we will be designing quantum circuits, so we analogously, okay, we'll have some quantum gates also. So there are certain quantum gates, okay, and via these quantum gates we can bring interacting qubits to nearest neighbor positions. More about fundamentals. Okay, so the qubit is a unique data element in quantum computing, analogical to a bit in classical computing. It is known as the quantum bit. Qubit stores superposition values of 0 and 1, which I've already explained, and the 0 and 1 are not shown, okay, in the usual manner, okay, when we are in the quantum realm. So the two possible basis states of qubits are 0 and 1. A qubit can be in this basis 0 state, okay, which is different from the 0 of classical bits. But this is one basis state, and this is another one, 1. So these are ones which get 0 and get 1. And when we measure a qubit can be in the 0 state. Its value of a qubit can be either get 0, get 1, or can be a linear combination of 0 and 1. This psi is used to represent the state. Okay, so this Dirac notation is there. This notation is called Dirac notation. So a state of a qubit is represented as a linear combination of 0 and 1. A qubit, okay, unlike classical bits, is never just 0 or just 1, because that is the potential of quantum computing. Every bit has to represent, okay, like more amount of information. So if with just one qubit, we can represent several possibilities of 0 and 1, okay, some amount of 0. That's why we have these two coefficients alpha and beta. So suppose we can say 50% of 0 and 50% of 1. That means the qubit is 50% 0 right now and 50% 1. Okay, or 40% 0 and 60% 1. So just imagine the potential of the information storage. So there are simulation-based systems or theoretical real systems wherein researchers have tried with storing 4 values using one qubit. See, with the bit we just store 2 values 0 and 1. But with one single qubit, they're trying 4 values, and they're trying to increase numbers. So as we increase this number, okay, which means allowing more alpha and beta values. So with one qubit, we can have several linear combinations of 0 and 1. So another interesting thing is that alpha and beta are complex numbers, and alpha square plus beta square is equals to 1. Okay, so the entire processing of this information, which I was all telling, can be summarized as behind the scene there is this use of quantum mechanical phenomena. There are different technologies, okay, so which I'll be telling about shortly. Now, what are the problems? Okay, so these are the problems: architectural limitations. So not even near-singular constant, which I just introduced. There are other problems. The problem is that there will be problem of noise in the surrounding atmosphere. Like inside a computer, conventional computer. Suppose like that, suppose we need some high frequency, okay, hearing device. So that's something that your speakers, right? There's some that or there's sound, things like that. So there will be an idea, okay, that the surrounding is phenomena. It creates the operation of the physical materials. Just now think about the atomic scale. So in a very controlled manner, okay, atoms or molecules are being used, okay, or different photons or magnetic fields are being used to represent. And if there is slight introduction of say wave interference, okay, high frequency waves interfere, or there is some like other kind of noise, okay, introduced during competition because of the quantum computing hardware from the matter of the device, okay, then quantum bits the things they are state, and the changes. Imagine that you something happens and the bits change, okay, for the files that are stored in the storage device. Okay, so that difficult is dealing with the bits. And then second problem that I mentioned is error detection. What is quantum error? So quantum just like considered principle that you try to measure the position of electron and then you get difficulty with its velocity. Similarly, if we have done some computation using a quantum circuit on a real quantum base, we try to measure ultimately after computation the values of the qubits. What will happen is that while measuring the values of the qubits sometimes may change, because if we spend a little more time in measurement, then that qubit will lose its current value, because it is always in a superposition of sigma 1, it will lose its current value. So we have to face this problem in quantum computation. This is another called quantum error detection. And then quantum error detection. Now how can we correct? So how can we correct errors? Because the coherence time for a particular state of a qubit is so short, so in fractions of seconds. So if indeed while doing measurement of qubit values, the qubits change their value, so the entire qubit will last about. No, we don't want that. So we want some correction mechanism. So one solution that recently we are trying is that for every logical qubit, that means we have a circuit diagram, let's say. So for every input in a circuit, we not just use one qubit, but we use multiple qubits. For one input of a circuit, so we use multiple qubits. So this will be copying the values, so keeping copy. So while measuring one and like that, so that increases the overload. So there if you can design some efficient algorithm. So suppose right now we have computers, some computers which are having having one IBM's computer that is having 15 qubits. So 15 qubits doesn't mean that the actual computer IBM's computer in the top there are 15 qubits only, not like that. So there will be many qubits for each theoretical qubit. There will be several qubits each keeping a copy. So this is very interesting research problem. This whole publication. How can we use minimum number of technical qubits to enable better state measurement? Right? And then these three points are fault tolerance, quantum fault tolerance. So even if there are errors in computation due to change in state for several reasons, the end result combination still should be correct. The big challenge. If you take a simple quantum circuit and there are say just 10 gates, only 5 gates, and after the second gate, suddenly because of some external noise, the qubit changes its value. So it's like our this database anomalies. So something was there for some data value X or something, and suddenly the value has changed. Now we have error computation. So that's about computation. So we design quantum fault tolerant computing systems. That's another interesting research problem. Then this is another problem. We just don't have one way of physical detection of quantum computing. There are several technologies. There is superconducting, there is ion trap technology, there is NMR, nuclear magnetic resonance technology. So then there are trap ion technology. There is trap ion technology. So I think 4 technologies: superconducting, NMR, and then this trap ion, and like that. Yeah. So there are different types of physical ways and technologies for realizing quantum computing systems. So different technologies come with different constraints. Now we can achieve this technology for conventional computers. Just one technology. Yes, there are different companies, AMD, Intel, Microsoft, no problem. But technology is one kind of technology. For memory, we have different technologies. So you can see we have this popular media, when the technology for running storage is different. We have this magnetic, related memory design for hard disks, and then we have RAMs, data design because AMD realizing so this technology. So realizing qubits for circuit design for quantum computing, we can use supercomputing technology, ion technology, or photonics, or say NMR. There are many others, and different organizations are using different technologies. For example, IonQ uses this trap technology. Whereas IBM uses superconducting technology. These are two different, and that's why the physical quantum computing on IBM systems is different from those for the IonQ quantum computers. Both are quantum computers. So every one of these problems that I listed here has possibilities to offer some more fundamentals. So now we talk about 2D and quantum motion processing and philosophy in doing. Now, what about quantum circuits? Quantum circuits are different from conventional circuits. So they consist of successive quantum gates. These are the quantum qubits. But the problem is that these gates require interaction of qubits. That means suppose if you have first gate and 2 qubits, and then there is another gate. If I can someone draw. That's it. Suppose you have so this is qubit number 1, this is 2, this is 3, this is 4. Now in conventional circuits, it's very simple. What we see is that there is a gate, and there will be some gate, and then this is output, then there will be another input, then there will be another gate. So this unity diagram in electrical hardware, they are all getting indicated, things like that. So in case of quantum circuits, you see these kind of diagrams. This is suppose control, then another gate between this. So these are fundamental gates showing, rectangular. So the third one, say like this, and so on. So just various 3 gates. So in case of conventional circuits, suppose we have to take this input, and there's another input. So we can do something like this. And if there is something that we draw also, we do something like this. Then we do something like this, and so on like this. These lines are not touching. So here they are touching. They are not touching. The circuit diagrams for quantum circuits are shown differently. These are for circuits for conventional computing. So here what we see the 2 circuits is different. Here the number of inputs 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the number of inputs and number of outputs can be different for conventional digital computer circuits. But for quantum computing, the number of inputs should be equal to the number of outputs. That's the basic principle of reversible computing. In reversible computing, as well as this principle. So energy is conserved in quantum computing. If you can design an ideal quantum computer, a lot of energy will be saved, there will be dissipation, and the number of inputs will be equal to the number of inputs, so that when we get the output of computation from the quantum circuit, we can get back the input, and vice versa. If from input, we will get the output. But from output, we get the input. Suppose here I get a 1. I cannot tell what was the value for 1, 2, 3, 4, 5. What was the value combination 1, 2, 3, 4, 5. These bits. Which can be pure number. It's only 2 bits. But when we are talking about circuit, so if suppose here the value is 1, 0, 1, 1, and then we get some other value, we say 0, get 1, something like that, and whatever output we get, from that output we can tell the input. That is how it's reversible. So now that if we can realize reversal computing, then ideally energy loss will be zero. But ideally then it's some energy loss. Okay, because zero phenomena can be quantum. Zero. Okay, this is reversible. So input always output. So it's like states, so we can sort of scale back and forth in time. Something related to heat and total theory of energy. This is it's not the same. Okay, there is also energy, every execution of gate, okay, that we see here. Okay, there is energy and there is execution, and finally after processing of these bits, okay, gate and send out the output, we will get some finally this output side. And we are so you can see that quantum studies are this. This first gate, this is they are shown like this. This is not touching. Remember, so very okay, so this is not touching. Here we show this kind of bombs, right? In conventional diagrams, okay? We quantum computing don't show bombs. So this called as okay NC diagram. So this is something it's little beyond the source discussion. Okay, so this is a succession of gates, and we can achieve parallelism also in quantum studies. You can see that if we can execute this gate between 1 qubit 1 and qubit 4, okay, we can execute the gate between qubit 1 and qubit 3. So these are the key advantages if we can actually achieve quantum computation. Okay, so each of these quantum gates operate on their qubits and can change their states. Okay, so these qubits every line represents a qubit. But the problem is with equivalence. That's a challenge. That suppose we started at time 0, so after say some 10 microseconds, the qubits value because like initially for this qubit 1 missing somewhere else. So if say some 500 gates, so after say 200 gates, value of qubit 1 can change. That's why we need backup or qubits. Okay, like lower. And sometimes, as you can see, these two qubits are apart. Okay, and they have to graph and made neighbors. So one of the questions of physical relation is the nearest. So here also we can research. It says that two qubits will interact in a way they need to adjacent to each other. These are all fundamental properties you can say, and also entering challenges for quantum computing. So it is circuits. So to overcome these problems of quantum computing, we need circuits. There's diagram of that later. And okay, the important ones of quantum computing. To move on adjacent qubits, adjacent qubits. Another important constraint, so this relation of circuits is that multiple gates. And it's here in this diagram we see that this particular gate and gate is able to accommodate multiple inputs. There are even 10 inputs if you want. Like we know the diagrams of of this multiplexers and things like that. So a gate in case of conventional computing can accommodate several inputs. That's not possible as of now for quantum circuits. Every theoretical quantum circuit that is presented to us for reduction, which may have theoretical quantum gates with multiple qubit inputs, have to be for the timing broken down into 1 or 2 qubit gates only for all the processes that have been introduced. So this also is another research point. We also in research involved. So if you introduce a quantum circuit, okay, that there is a multi-qubit quantum gate, okay, that is called powerful. And there will be there are other multi-qubit like gates, quantum gates. So they cannot be realized as it is in the hardware. They have to grow it breaks down to 5 fundamental 1 and 2 qubit gates in active quantum circuit relation. So this is another one, right? So this is diagram of circuit. This is the overheads. They say that if qubits are not adjacent for real quantum devices as of now, they are available in the cloud from different organizations. So we need to introduce more gates. So if we introduce more gates and the qubit lifespans are shorter, so that increases the problem of coherence. That magnifies the problem of qubit coherence. So we need to do more backup of qubit values. So these are the problem of quantum computing. And this CNOT is a very important gate. This is also passed on because every swap gate with residues that can be realized in 3 CNOT gates. So if you have circuit quantum circuit are 500 gates and we introduce 200 swap gates, so then we introduce 600 additional fundamental CNOT gates like that. So okay, imagine the difficulties right now we are facing. Now with all these problems are like prevalent, we are still doing quantum computation. Okay, and IBM's QI skit, okay, skip all these sometimes. So that is available that everybody can download and use because it's open source. Okay, it will just do some and that gives support for designing quantum circuits for different applications. So as I was saying in the beginning, that circuit design is a key problem also in research area. So quantum computing speeds up computation. So that's why suppose there's a universal algorithm and we can speed up using quantum computing. So we can application specific quantum circuits. That's why we hear this term quantum machine learning, quantum information security flow, quantum cryptography, things like that. Suddenly, basically people first consider in the mind. Then instead of designing conventional, like silicon, like technology-based conventional circuits, if people design quantum circuits, okay, why first designing in the soft form, like architects or designing a sketch. So we can do this speed from IBM for designing this. Okay, like soft form of this circuit. So we have to do some solving of machine learning problem when we need to certain states. So we design circuit, circuit for searching. Okay. And then we will try to simulate that in the different real hardware devices and serial phones. Then every other organization which introduce their hardware phones have also their individual software running. Okay, and even any of them are working collaboratively because in case of us also, IMD for example, it is taking support of device kit as well as it's embedded software for its hardware, which is IMD based. And IMD is based on like superconducting. So if you have to clear the whole dimension, then the side will not be text only. And then there's a matter of gate leveling. Now because I said we design circuits, so how do we design circuits? Just like for classical computing, we need NOR and NAND universal gates. We don't have to individually use OR and this AND gates things like that. Similar for quantum computing also, these are universal gates, gate libraries. Okay, so the 3/4 plus T library is for real circuit design. The other 2 are for logical circuit design. So as I said, what is the idea of quantum in computing exploration? That we first design real circuits for application specific tasks, okay, and speed up the computation, and then we give them a real form by using real quantum gate libraries. Right, 3/4 plus is one such library. So now this is summary. There are different quantum hardware devices available depending on the different technologies. There are technology. So different organizations are introducing different quantum hardware devices. They are even startups, okay, putting funding and then using these different computing devices. Based on different technologies, there is relation. So we have the currently quantum hardware we can use. We do some registration sometimes that charges normally also 22 years license for using and experimenting the service that we design. Okay, and what IT designs that provide quantum hardware support, IBM and Google, you can really please select their main ones. Thank you very much for your question. Questions?
Thank you, sir. If the person has any questions, then you can ask.
Yes.
If the person has any question, then you can ask Dr. Sakura.
Sir.
That was speaking always, also. Yeah, please go ahead.
Great.
Then you can speak on it. It doesn't really there is as such no like high performing concept of quantum memory as yet developed. It is very fault tolerant and robust to the coherence. So try to understand that persistence, right? Information has to be intact, it has to be persistent. So there has to be the introduction of robust, fault tolerant, highly performing persistent technology for quantum information storage. Okay, and then adding to this point, I'll comment that a qubit doesn't store only 0 and 1. A qubit stores a superposition or linear combination of different degrees of 0 and 1. Right? So it's like many values by one qubit. Okay, and each value is shorted. So that's why the memo concept for quantum information storage, is still a big problem. So as I said, we have to bring in the qubit to ground state and find out from that can be stored in conventional memory devices. That's the issue. But during computation, storage and the factors, talking something that will get qubit. So that's like big application in the market. Information is shorted. I hope that helps. Okay.
Any question from participants?
Any question? Participants, any question? One question to from my side. Quantum computation of quantum computer. Definitely introduce many algorithms. Faster transition from the classical computer to quantum computer. Even RBC algorithm also without reading that RBC algorithm not working quantum computer. So a new quantum computer is security algorithm must be developed. So please tell me about that. How much time will take for this condition?
Yeah. So there are two aspects. First is regarding the transition, second is regarding security. So what you said is correct. Regarding transition, there may be notion. I don't know. But notion is not that quantum computer will replace conventional computing. That's what I was telling the talk. That quantum computation should be seen as a kind of co-processing support. Just like we are using the system for gaining more computing power. So similarly, with the peculiar advantages of quantum computation, we can add up in computing power for conventional computers. So that's the thing. So it's not transition basically. It's an addition and then comparison of two different worlds of computing and seeing which works well for what problem. Sometimes conventional computing will be a better choice because we have to do so many physical problems, noise and coherence problem for quantum information. Second thing regarding cryptography, we have this information that the present cryptography system relation RSCs and things like that. So they will be broken up. That is perfectly okay. The point is that if it's not the proper like social organizations, for instance, private items, but it's suppose a team of hackers. They get access to they harness quantum computing. And they develop a very good quantum computer, which understand by having things like that. If they start breaking the large numbers, so many of the online transactions that we are doing, those mechanisms will be rendered insecure. That's why we have to work with quantum cryptography algorithm, and many works have already been done. QKD is a quite host of quantum key distribution and quantum cryptography, and quantum cryptography algorithms are practically impossible to break. Okay, and others we hit why this so because we have the problem of decoherence. So this decoherence and the need for doing entanglement for qubit measurement, that is a very short time activity. So that makes the eavesdropping the information extremely difficult. So that's a good thing.
Thank you all.
Thank you. So I think we
have one listener on MD also on security, Dr. Chulendanath. Do we have a question to Dr. Chakraborty on security?
no, sir.
Muni, so on the Department of Computer Science, we would like to say thanks to Dr. Chakraborty for giving us time in this webinar, and I hope all participants have got or come know what is quantum computing and what are the technologies. So we like to say thanks to Dr. Alok for this wonderful presentation.
So can I put now for some time?
It's really a good discussion, and our participants must know some insight about this research of quantum computing. I think we represent first basically working on this research. So now we have our second session by Dr. Nicholas, Assistant Professor, Department of Computer Science and Engineering, IIT Rouen. She will be discussing low hammer attack on medium main memory. Dr. Rakesh Kumar will be moderating the session. So may I request Dr. Rakesh Kumar to introduce the session lesson. I hand over to Dr. Rakesh Kumar.
Muni, wait for Dr. Shitu is trying to join. We have to take this. Last time is a girl bomb, so we have the session taken before time. So that's why you wait for
yes, wait for some time. We'll let you know once the session is selected.
An announcement to the participants these in the attendance form site is available in the WhatsApp group. So you click up and open directly mandatory for all of you. So our next speaker, Dr. Taj from IIT Roper, has already joined in the meeting session. So I would like to request Mumi to continue the session.
This session is continued by Dr. Rakesh Kumar and I will be moderating session. So I request Dr. Rakesh Kumar to introduce Dr. Shitu. Over to Dr. Rakesh Kumar.
Thanks, Muni. Good afternoon, everyone. It's my great pleasure to inform you today our next speaker, who is Dr. Silchar Das. He is our only student. He has done Master of Computer Science from Assam University in 2007. Then after he moved to IIT Guwahati to pursue its MTech from that MTech in Computer Science and Engineering. Then after he has completed his PhD from that institution, it is from IIT Guwahati in 2016. Then after he joined the IIT Guwahati, and after that he has now in the present time he is currently serving the Department of Computer Science, IIT Ropar, as an assistant professor. So he will be delivering the lecture on raw human hammer attack on DRAM-based memory. So with this word, I invite Dr. Sedudas to come and to enlighten us with this lecture. Thanks.
Okay, thank you, Dr. Dr. Rakesh, my voice is audible?
Yeah, you are very much audible.
Okay, thank you for the nice introduction, and thank you, the organizers, for letting me for this talk. So, let me share my screen.